5 functional groups we'll be covering in this chapter. That's quite handful, okay? And of these, the alcohol thiols are basically similar, and ether. So basically, majority of the compounds, alcohols, aldehydes, ketones. So if you think of water, so this is our water, okay? Now, if you replace one of the hydrogen, so if you replace one of the hydrogen and put a R group, R means a alkyl group, okay? Any hydrocarbon group. So that becomes an alcohol. So basically you can think of alcohol as a derivative of water. And if you replace both, so this is an alcohol, if you replace this R also and get a R, we get an ether. So what is unique about water is the hydrogen bond. So as you are replacing the hydrogen with the alkyl group, you are losing the hydrogen bond. So alcohols still can do hydrogen bonding because it has one OH, and the ethers cannot. Okay, so the properties that we'll see for these compounds will reflect this phenomena. So alcohol, phenols, ethers are compounds of oxygen of the type ROR. If one of the group attached to the oxygen is hydrogen, so that's an alcohol. Now, phenols are alcohols, but if the R is a benzene ring, okay, that's called a phenol. And if both the hydrogen attached to the oxygen are replaced by hydrocarbon groups, that's an ether. Now, thiols are basically, thio means sulfur. Okay, so whenever you see the name thio, that's sulfur. So instead of OH, if it is SH, okay, if you see SH, that's a thiol. Now, naming alcohols, scientific name of alcohol is named by replacing the E with an ol. So ethanol, methanol. So you take the alkane name, take away the E and put a ol. Okay. So this is Arabic naming style. Now, alcohols, they also have this common name. Now, for the common name, you write the aisle name, methyl, ethyl, and end with an alcohol. Okay, so now you have to know the common names also, some of the few, okay, very common names. So we use the alkyl name, alkyl group name, followed by alcohol. So methyl alcohol, propyl alcohol, isopropyl alcohol. Okay, so these are the common names. So you have to know the common names also, okay? So alcohol, phenols, thiols, and ethers. When an alcohol consists of a chain of 3 or more carbon atoms. So these are some of the common alcohols. So and alcohols and ketones, these are very, very common all around you. So for namings, you just take the alcohol, the alkene name and add a all to it. When alcohol consists of 3 or more carbon atoms, the chain is numbered to give the position of the all. So the alcohol OH can be in position 1, 2. So these are what we call the constitutional isomers. Okay. Or functional, and then you can also have the functional isomers where you can think you can make it a ketone and they'll have the same formula. So to name this, you put 1, 2, 3, and then have to show VAT. So 2-propanol. Okay. So when it's cyclic alcohol, you really don't put the numbers because it's not necessary. Everything is 1. But if you have second substitutions, then you have to put number, and you start the numbering from the alcohol group, carbon containing the alcohol. Okay, 1, 2, 3 and so on. Now, naming phenols. So when you want to name the phenols, the phenol is the root name. Remember, and there are 4 compounds that are basically IUPAC names. Okay, so phenol, aniline, and then toluene. Okay, so phenol is the IUPAC name of the benzene ring. When there is second substitution, uh, the benzene ring is numbered starting from carbon atom 1, 2, 3. So 3 chlorophenol. Okay. So guide to naming alcohols, name the longest carbon atom attached to the OH group by replacing the E with an ol. And number the chain starting at the end near to the OH group. Give the location and name of its substitutions. As an example, if you want to name this, you go 1, 2, 3, 4, 5. Okay, so you are basically numbering and giving the OH the list number. So this is 5 means pentanol. Where is the ol? 2. So 2 pentanol. And the substitution methyl where? 1, 2, 3, 4. So 4 methyl 2 pentanol. So if you want to name this, you will go, this is a phenol. So start with the carbon with the containing the OH is number 1. And you have to go clockwise because that will give the bromine the list number. So 1, 2, 3, 4. So 1, 2. So this is 2-bromophenol. Now you can also say ortho-bromophenol. Remember ortho metapara. Okay. So you can also say ortho. Is that clear to everybody? 2-bromophenol is ortho-bromophenol also. Give the IUPAC name 1, 2, 3, 4. So this is a butane, and alcohol is at 1 position. So this one is 1, 2, 3, 4 is a butanol. 1 butanol. Okay. 1 butanol and 1, 2, 3. 3 chloro, 1 butanol. And the next one, that's a phenol. So phenol at 4 position, you have a methyl. So 4 methyl or para, you can also say para-methyl phenol. Now, you can also name it as toluene. Okay. So para-hydroxytoluene. So you can either take this as a root name, but since phenol is the predominant, more predominant group, functional group, usually that is what we keep, the phenol. Okay, so this is 4-methyl phenol or para-methyl phenol. So thiols are basically alcohols. With a SH. Instead of OH, you have a SH. And the properties are close, but little bit less reactive. And thiols do not have a hydrogen bond like OH. So, and their name similar, you just add a thiol. So methanol, methane thiol, ethanol, ethane thiol, and so on. Okay. Now, these compounds, they are basically, found in some of these. They have a strong smell. Okay, and bad smell. Usually, thiols are associated with bad smell, like the skunk spray, onion, garlic. Okay, and the other H2S itself has a rotten egg smell. So these are for the thiols. Ethers, the ethers, basically replacing both the OH with the alkyl group. And important is naming ether. Okay, so you identify ethers when you say the 2 alkyl groups on 2 sides. For naming ethers, you name the 2 groups attached to it and end with an ether. The IUPAC name is, you say alkoxide. This is a common way of naming. Okay, common way of naming is you take the alkyl groups and you say ether. And the other way of naming is alkoxide. That means ethoxy, ethane, propoxy, propane. So we can also name this as methox. So this is the bigger group. So propoxy, okay, propoxymethane. Like if I have something like this, uh, ET, ET is ethyl group, ETO, ET. Okay, so we can write it as diethyl ether. Okay, diethyl ether. That's the common name. Okay, diethyl ether. They always end with ether. But we can write this as ethoxyethane. So alcohols are classified by the number of alkyl groups attached to the carbon atom bonded to the OH. So before, okay, so the other thing about the naming ethers, remember, you have to put them in the alphabetical order. Okay, uh, right, if you are doing it in the common naming style, so propoxy, methane. Uh, uh, so here, if you're writing methyl propyl, so M comes first, then P, methyl propyl. Okay, methyl propyl ethane. So in that case, for the Arabic name, probably we'll go methoxypropane. I think that let's keep it like that rather than this one, for proximity, because I was going by molar mass. That's another style. So let's keep it to one. If you are not asked anything, then you will just write methyl propyl. But if you are said that you give the common name, this is the common name. Okay. So IPEC accepts the common name, but IPEC have his own style. So and that is basically the propoxy or methoxy. Okay, oxy, like diethyl ether. That's the common name. Okay. But if you are asked to give a name and asked to give an IPEC name, then you should write this as ethoxy, ethane for this same compound. Now, ethers, the properties of these compounds, alcohol's property depends on the OH group. Okay, primary alcohol, secondary alcohol, tertiary alcohol. There are three groups of alcohols we can get. Now, that depends on the number of carbon attached to the uh, carbon containing the OH. So if you look at the carbon containing the OH, so this is the the alpha carbon uh, right here. This one is the alpha carbon. The carbon and then you look for how many carbons are there attached to that carbon. So if there's one carbon atom attached to that, we say primary, 1 degree. Two carbon atoms means 2 degree, and 3 degrees, three carbon atoms. Okay. So classifying alcohols. So if you look at this structure here, and classify each of the following alcohols: primary, secondary. A. What do you think? Oh, the answer is given. That there's one carbon atom attached to this carbon. So what do you think this is? This is a primary, right? So B. If you look at, so you are looking at the carbon that is attached to the OH. Yeah, so right here. And then you can see the three carbon atoms attached. So this is a tertiary. If you look at this ring carbon atom, and you can see two carbon atoms attached to this carbon. So that's a secondary carbon. That's a 2 degree carbon. So primary, secondary, tertiary. This is a name that will come across quite frequently during this course. Okay. Solubility of alcohols. Alcohols, if you think of alcohol, the two parts in the alcohol. Okay. So there is this hydrophobic group and this OH. So this OH is polar, the rest is non-polar. So if the alcohol is small, so overall the molecule will be polar and it will go into solution. So methyl alcohol, ethyl alcohol, so all the way up to 4 carbon atoms, alcohols are soluble. Isopropyl alcohol is soluble in water. But starting butanol is partially soluble. So let's say uh, from pentanol onward, this backbone non-polar part becomes predominant, and the alcohols start to become insoluble. Okay, so after 5 carbon atoms, alcohols are not soluble. So the solubility of phenols. So if you think of phenol, that's a benzene ring, right? So the six carbon atom. So six carbon atom, that's why it's slightly soluble. It's not very soluble, but slightly, because the OH group can form hydrogen bond with water. Okay. Now phenol, we'll see phenol. That phenol, is more polar than other alcohols because of this it delocalization into the uh, benzene ring. Okay, the hydrogen bond is strong enough to break the OH bond, and that makes phenol a acid. The phenol, also called carbolic acid. Okay, and the reason it can behave like an acid is you can see this OH, and this is only for phenol because this phenoxide ion it can delocalize. This electron can delocalize into the benzene ring. So the benzene ring and benzene ring is like well, it delocalized. So there are three double bonds, right? But it's not actually three double bonds. It forms a ring. It's like all the six p orbitals are delocalized. It's like a giant sink sitting there. Okay, so that's why benzene has a different chemistry than rest of the alkanes. But this phenoxide ion, when generated, this negative ion gets stabilized by delocalizing to the benzene ring. Okay, and that's why phenoxide ion stable and phenol acts like a slightly acidic compound. So commercially is known as carbolic acid. Aldehydes and ketones contain a carbon-oxygen double bond. Okay. Uh, Now carbon-oxygen something like this. So this double because of the double bond, this is polar, and these are called the ketones. Now, the if along with this C double bond O, you have a hydrogen, like in the picture on the left. Okay, this one. So that's called an aldehyde. So you have the aldehyde, you have the ketones. Okay. The double bond in the carbonyl group is similar to that of alkene, but is much more polar because oxygen is in an electron withdrawing group. It'll pull the electron towards itself, making that bond highly polar. The polarity of the carbonyl group strongly influences the physical and chemical properties. So, and because of that, you can see the chemistry is dictated by this polarity of this bond, and the carbon is slightly electropositive, so something negative is going to attack this carbon atom easily. Okay, and something positive will attack the oxygen. The aldehydes and keto groups can be written as a separate atom uh, or as CHO or CO. So when you write it as a condensed formula, you can basically write this as CH3CO CH3, okay, or CH3 CH2 CHO. Now, for naming aldehydes, okay, uh, for so aldehydes, you end with an al. So take the root name and end with an al. Now, aldehydes, see, aldehydes, there's no, aldehydes can only occur uh, at the end of the chain. It cannot occur in the middle of the chain because it needs a hydrogen. Okay. So aldehydes are, we do not need to put numbers on the aldehydes because it's always at the end. So no number is needed for the aldehydes. Okay. The aldehydes with carbon atom, uh, uh, aldehydes with carbon chain of 1 to 4 are referred with the common names. So for the first 4, you end with an aldehyde. Okay, formaldehyde. Okay, again, formal is one carbon atom, two carbon atom acetaldehyde. Okay, propionaldehyde uh, and butyraldehyde. So you always end with an al. So that's the common way. Now IPEC system of naming is you just end with an al. So methanol, propanol, butanol. Okay. So if it is a benzene ring, we call it benzaldehyde. Now this is taken as the IUPAC name. There is one other compound here, which is the IUPAC system. Okay, uh, benzaldehyde. That's actually the common name. Okay, common name is accepted as the IUPAC name. So any derivatives of benzaldehyde can carry this as the root name. So naming aldehyde, just put an L. Okay, so you first name the main chain. So main chain is 1, 2, 3, 4. Um, so this is butanol with a methyl substitution, 3-methyl butanol. Ketones. For ketones, we take the root name with the own. Okay, ketone, propanon, pentanon, and so on. But where ketones can occur at any place, not at the end, but any place in between. Okay, a non-end carbon atom. Uh, so, like propanon, butanon. But here, when you're doing the pentanon, you have to say where. Okay, so butanon we do not need to because there are only 2 positions available and they are the same. Okay, so for butanon, you don't need to say the position, but with the pentanon, yes. Now, you can also name it like the common style. Okay, the common name of the ketone, uh, like propanon is dimethyl ketone, ethyl methyl ketone. So these are the common ways of naming these ketones. So guide to naming ketones, name the longest chain by replacing the E in the alkane with an on. Number the carbon chain starting from the end near the carbonyl group and indicate its location. And name and number any substituents on the carbon atom. So if you want to name this, then you are going to start right from here. So if I annotate, so this is where you identify the main chain, then you start the numbering, giving the ketone the list number. So 1, 2, 3, 4, 5. So that's 5 pentanon, 2 pentanon. Okay. And where is the methyl? At 4 positions. So 4 methyl, 2 pentanon. What is the common name of 3-hexanon? Okay, the common name for 3-hexanon, if you want to do it, 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3. So this is where our double bond is. Okay, the groups attached is this one and this one. So this is a propyl and the other one is ethyl. So E comes first. So ethyl propyl ketone. This is the common name of this ketone. So properties of aldehydes and ketones. And aldehyde ketones, they are partially soluble in water, like acetone. So many of you know acetone. Okay, we use it commonly for many, as a paint remover, nail polish remover, and so on. Because of the hydrogen bonding, aldehydes and ketones from 1 to 4, just like the alcohols, they are very soluble in water. Longer carbon chains increase the non-polar nature and the solubility decreases. So after butanol, basically, it doesn't want to go into solution. So pentanol, slightly soluble. It's almost like the alcohol. So why is acetone soluble in water, but 2-hexanon is not? Because it becomes more non-polar. Okay, with the 2-hexanon. Acetone contains a carbonyl group with an electronegative oxygen atom that forms hydrogen bond with water. Hexanon also contains a carbonyl group, but its long non-polar hydrocarbon chain makes it insoluble. So the contribution from the non-polar part becomes too high. So give the common name. So this is acetaldehyde. Okay. This is formaldehyde C. B is methyl and the other is 1, 2, 3 is propyl. So LM NO P. So M comes first. So methyl propyl ketone. And methyl, so you can do that. So for the cyclic ring, you start the numbering from this ketone here 1 and go clockwise 1, 2, 3. So you have a substitution at 3 and 4. 1, 2, 3, 4. Yeah, 3 and 4. So 3, 4 dimethyl cyclohexanol. 3, 4 dimethyl cyclohexanol. So this is a benzaldehyde. So 2 bromo, 2 bromo benzaldehyde or orthobromo benzaldehyde. So alcohols, they are used as fuel. So if you burn alcohols, you get carbon dioxide and water, okay, with energy. So we use that as supplement for gasoline. So 20%. So nowadays all the gasolines are mixed with alcohols. Dehydration reaction is just the opposite. Okay, so alcohols, if you eliminate water from alcohol, that means HOH, you are eliminating this water, HOH. So when you're eliminating this, then you are forming a double bond. Okay, so alcohols give alkenes, okay, when upon dehydration. Alkenes on hydration gives alcohol. So this is minus water. Okay, alcohols give alkenes always. Okay, please remember this. And alkenes give alcohols if we add water. They're related to one another by this relationship. Dehydration of alcohols. Alcohols undergo dehydration reaction, giving alkenes. The H and OH are removed from adjacent carbon atoms of the same alcohol to produce a molecule of water. Now, if you remove the hydrogen and oxide from two different molecules, then you get an ether. Okay, so if you remove water molecule from two different carbon molecules, okay, so and let's say another one is, I'm just writing the molecule just a little bit turned around. So R prime, and now if we remove from two different molecule, what you get is the ether, R O R dash. So when removed from the same molecule, you get an alkene. And removed from two different molecules, you get ether. Okay, draw the condensed structural formula of the alkene produced by the dehydration of the following. Okay, so CH3, OH, CH3. Now these are all symmetric. Okay, so that means you don't have to choose which hydrogen you are picking up. So in this case, you can write this as CH 2 double bond, okay, CH and CH3, or you could have done from the other side also. You could have taken the double bond, but they're same molecule. So you could have also got this. You really do not have to make a choice there. But what if we have to decide? Okay, if the molecule is not symmetric, so you always get the more substituted alkene. So in this case, we don't have to bother because it's symmetric alkene. But otherwise, we always have to look for the more substituted alkene. That's the most stable product. What is the name of the alkene produced by the dehydration of cyclohexanol? Well, cyclohexene, right? So is that clear on the dehydration? So if I give you a asymmetric alcohol, then always the product will be the most substituted one. So as for example, if you get something like this, if this forms an alcohol, then your product would be rather the double bond will form. That will give you the most substituted one. So you'll get two substitutions here, but if you put the double bond here, you get more. So this will be the more preferred product because this is the most substituted one. Okay, not between this. That is not formed because that is the less substitutions. This is called the jet-shape rule. Okay, so reactions of alcohol. So we saw combustion is a good reaction, right? Burning. Dehydration is another one. Combustion, dehydration, and now oxidation. Alcohol oxidation in organic chemistry, oxidation means addition of oxygen. So if you look at the carbon-oxygen bond, if there's an increase in the carbon-oxygen bond, we call it oxidation. So oxidation involves addition of oxygen or loss of hydrogen. That's another thing, loss of hydrogen also. And also in biochemistry. So those of you who wants to go into microbiology, biochemistry pathway, you will come across oxidation reduction in a lot. But there, the concept is, the concept is same, but we more relate when we write this book, we more relate to addition of oxygen and loss of hydrogen as oxidation. So if you look at this, alkane, like it's like a one thing. Alkane, if oxidized, you get an alcohol. Alcohols, when oxidized, give an aldehyde. So how do you know it's oxidation? Because instead of one carbon-oxygen bond, you have two carbon-oxygen bond. Okay. Aldehydes on further oxidation gives a carboxylic acids. So if you start with the primary alcohol, if you look at the second part, primary alcohols on oxidation gives an aldehyde, and the aldehydes further oxidized to give a carboxylic acid. Okay, but if you start with the ketone like this, okay, or secondary alcohol, if you start with the secondary alcohol, they give ketone and they cannot do anything else, right? It stops there. So this we can use a test for aldehydes and ketones. So aldehydes can go all the way up to carboxylic acid, but ketones cannot go any further. Okay. And see how the oxidation is happening. So as I said, addition of oxygen or removal of hydrogen. So it's basically hydrogen removal. That's why it's oxidation. You need 2H to get the double bond. Okay. So there are 2H here on adjacent. So one on oxygen, another on carbon. Okay, and you get the aldehydes and the ketones. So when you go from aldehyde to ketone, you're adding an oxygen in between the CH. Okay, so you cannot do that with a ketone. So it stops there because it can do that with the OH, but not on a carbon. Okay, so the secondary alcohol. So tertiary alcohol. So primary will react, secondary will react and go up to ketone. Tertiary alcohol, 3-degree alcohol, do not react at all, do not undergo oxidation. So if you have a reagent, let's say colorimetric reagent, which changes color, we can use that to test this 1-degree, 2-degree, and 3-degree alcohols. Okay. So reaction of alcohols. So now reaction oxidation of thiols. This is very important. So thiol. So I will definitely get one question from here, because thiols are, as I said, like alcohol, but this is the difference here. Thiols, when they oxidize, they form this SS linkage, okay, disulfide linkage, and this is a very important chemistry in nature, okay, in the cell, and so again, this is a chemistry for nursing. So I expect many of you to move into those fields, and there will see proteins. So cysteine can form protein cross-links using this disulfide linkage. So remember, thiols, that means cysteine, upon oxidation, they form the disulfide linkage. So this is sulfur chemistry. Okay, and they serve like a protein cross-link. Insulin has a disulfide linkage, by the way. Tollens reagent. So this is one of the reagents. So there are two reagents that we use for the aldehyde ketones. One is the Tollens and the Meridix. Tollens reagent is ammonical silver nitrate. So ammonical silver nitrate, if you add into an aldehyde, it still get oxidized, but reduces the silver ion to silver. And silver, when deposits, give a silver mirror. So if you look at the test tube side, you can see like a very shiny silver mirror. We say the silver mirror test. Okay, so aldehydes form the silver mirror, but ketones don't. So that's a nice test for aldehydes and ketones side there. Okay. Now, Meridix test is something similar, but for Meridix test is basically a copper sulfate. So copper sulfate solution. So copper sulfate, if we add now this, so for this aldehydes with the adjacent OH, so they must contain. This is very important. So it must contain this adjacent OH, okay, along with this aldehyde. So that have aldehyde with adjacent hydroxyl group. And so 2-hydroxypropanoic acid works, but most importantly, the carbohydrates. Okay, this carbohydrate is a nice test for the carbohydrates. All carbohydrates have this OH adjacent to aldehydes, glucose, fructose, mannose, all of them. Okay, so this is a nice test for the aldehydes. Very, very important test. And you see a brick red precipitate forming. Okay, if it is reducing. So okay, so we'll see that in the carbohydrate chapter, we can have two kinds of carbohydrates. We can have reducing carbohydrate and non-reducing sugar, non-reducing and reducing sugar. So that's the two big classifications in the sugar group, and we do that using this Meridix test. So these are oxidations. If we reduce, of course, you get in the alcohol, the other side. Okay, so if you reduce the alcohol, you are adding back the hydrogens. So what you get, which is basically an alcohol. Okay. Reduction of carbonyl groups. So, if you reduce this ketone, so always remember when you're reducing it, you're basically adding hydrogen. So you are adding one hydrogen here and another hydrogen here, but this double bond will be gone. So this double bond will be gone. Okay. So instead you are adding this hydrogen. So whenever you try to make a product, think of it like that, addition of hydrogen, because that is what you're doing. Hydrogen, you're adding hydrogen is a nickel catalyst. Draw the condensed structural formula for the dehydration. Okay, dehydration is just from a double bond here, right? So when you are dehydrating this, so this HOH, so hydrogen will go from this. So together, if we eliminate this water molecule, so you get a double bond here. Okay. So here too, we can imagine now. This is all symmetric. So symmetric is easy. Is asymmetric? Remember, you choose the most substituted one. Here too, the double bond is formed here, and you are basically eliminating a hydrogen from all of these. Okay. So these are all dehydration reactions. 1, 2, 3, 4, 5. 5 functional groups we have covered in this chapter. Okay. Basic thing though, nothing hard, but they will come useful. You will see in later part or whatever we do later on. This is the common ones, and apart from them, we have the amines carboxylic acid, which will be another chapter we'll cover later. Okay, so now alcohols. Alcohols are there. The cholesterols, alls. Okay, cholesterol has this, alcohols. Thiols, this amino acids contain thiols. Ethyl linkage is found in the carbo, all the starch, glycogen, they contain this ethyl linkage. Aldehyde ketones, they appear in the sugars. Okay, so the sugars that we have, the glucose, galactose, mannose, they are fructose, they are aldehydes and ketones. The chemistry that you see for the sugars, okay, depend on this. It's very, very important functional groups. Okay, so we covered the thiols, alcohol, phenols, ethers. So alcohols upon dehydration gives alkenes. Alcohols upon oxidation, so alcohols can oxidize. So if you oxidize alcohol, you get either aldehyde or a ketone, depending on what kind of alcohol that is, 1 degree or 2 degree. Aldehydes can further reoxidize to give carboxylic acids. We also saw phenols and ethers. So phenols and ethers, phenols are slightly acidic, and that's because of the delocation of the phenoxide ion into the backbone, phenyl backbone. And we also saw naming. So of the naming of ethers, you are like methyl, butyl methyl. So always you write the alphabetical order and then ketone. Or you can write the IUPAC system, ethoxypropane, methoxypropane. Okay, there are two styles. And this is a summary basically, uh, how to name them. So common name, and we have the IUPAC name. So when you are doing that for the ether, IUPAC name is empty here. So if I write IUPAC name there, you can write it again right now. So it's a methoxymethane for the example on this chart. So please write it down there on that empty space. Methoxymethane. All right. So these are summary of the reactions and important ones, not everything, but important ones. Combustion always gives you carbon dioxide water when they burn. Dehydration means elimination of water. And right here, you can also, write it forms a more substituted. Okay, if it is asymmetric. Okay. And that's called the jet-shape rule. Okay, so oxidation of primary alcohol to form aldehydes. So primary alcohol, but it doesn't stop, remember, the aldehyde state. It's hard to stop them at aldehyde. So all the goes all the up to carboxylic acid. Okay, for 2-degree alcohols, they give ketones, and 3-degree alcohols do not undergo oxidation. So aldehydes can further reoxidize to give you the acid. Okay. And if you reduce the aldehydes, that means you are adding hydrogen. You get back the alcohols. Okay. So if you add hydrogen here, you are getting primary alcohol. Okay. Aldehydes give primary alcohol. Ketones give secondary alcohol, 2-degree alcohols. It's just the opposite.